Hello, good evening to all the participants.
Good evening.
So, I think we can wait for a few minutes for some more of them to join. Anyone who is joining the live interaction session for the first time who didn't join last week, please feel free to introduce yourself.
Hello.
Hello.
Yeah, I'm Vidyadhar Kakodkar, consulting civil engineer.
Okay.
Actually, I joined the course late last week. Only I joined the course.
Okay.
So
Okay.
this is the my first an interactive session.
Okay. Welcome to the course.
Thank you, sir. Thank you very much.
Yeah. So, where exactly you are from and where you are practicing?
I am from Goa. I am practicing in Margao, Goa.
Okay, okay, okay. So I think reinforced concrete, is a prevalent uh, construction typology, right?
Yes, sir.
Yes.
We are
So
doing a 90% of the structure in our reinforced concrete only.
okay, okay. So up to what story, building design you are doing?
We are allowed to around 10 story only in Goa.
Okay, okay. I guess because of the wind loads, right?
No, no, there are restrictions, planning restrictions.
Oh, okay,
At
okay,
latest planning restrictions will allow us till 15 floors, but that is not yet implemented.
okay, okay. Okay, nice to have you. We have a certain multiple choice question planned for this session. I hope you will find it interesting and informative.
Yes. Yeah.
Yeah. Anybody else would
Okay.
like to introduce? So it is 7:06 p.m. right now. So I guess we can wait until 7:10 and then we can start the discussion as usual. So in the meantime, if any of you have any questions regarding the week 1 lecture or the week 2 lectures that we have seen, uh, please feel free to ask. I will be going over the week 2 lecture slides once again. So I hope all of you have watched the week 2 lectures, that is based on the materials, concrete, long term, short term properties and reinforcing steel. Hello.
Yes, sir.
Okay,
Yeah.
okay, okay. So we will start the live session very shortly at around 7:10. So welcome back to all of you. We will go ahead with the interaction session. So before starting the session, I would like to introduce myself. So this course is presented to you by NPTEL. The name of the course is Advanced Reinforced Concrete Design, and the course is instructed by Professor Surya Prakash. I'm sorry, I think I should have started sharing the screen first. So one of the requests to I hope my screen is visible now. Yes, can any one of you confirm? Okay, so yeah, so what you can do is you can unmute yourself and you can speak up, because sometimes when I'm in the presentation mode, I might not see the chats or the messages that you're typing. So feel free, all of you. This course is designed for you, and we'll try to make it a very nice interactive session. So I hope my slide is visible now.
Yes.
So the course is being taught by Professor Surya Prakash from IIT Hyderabad, and this is our second live interaction session. And a brief introduction about myself. My name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow working in the Department of Civil Engineering at IIT Delhi, and I'll be the teaching assistant for this particular course. And we have planned for a total of 12 interactive sessions. So this is the interaction session based on week number 2 of the lecture series. So the protocol of this live interaction session would be such that firstly I'm going to present a summary of the lecture that was being hosted on the website this week, and then that would take around 15 to 20 minutes, and then we are going to start with the multiple choice questions. I have designed around 20 questions for this week based on the three modules three parts of the module that we saw in the lecture. So without any further delay, let us start with the summary of the lecture. So whenever there is any doubt, please feel free to unmute yourself and discuss any doubts that you have with me. Okay, so we are starting with the part 1 of the module. I hope that my screen is visible now.
Yeah.
Yes. So in this particular week, we looked at 3 parts of the module. So the first part of the module consisted of the short-term properties of concrete, that is broadly the stress-strain behavior and the constitutive relationship. And then in the second part of the module, we looked into the long-term properties of concrete, such as shrinkage, creep, which usually comes up after a prolonged period of time. And then in the third part of the module, we looked into the properties of reinforcing steel. So these are the learning outcomes in the first part. We looked at the different constituents of concrete. Then we looked into the behavior of high strength concrete and normal strength concrete. What are the difference in the properties between these two types of concrete. Then we looked into what are the properties required in order to qualify as a lightweight concrete, and how it has been developed and what are their advantages. Then we looked into the composition of cement and the different types of cement. Then we looked into the process of hydration of cement and the process of hydration of the different constituents that make up cement. Then we looked into the stress strain behavior of concrete under compression as well as tension. Then we looked into the behavior of concrete under the multi-axial stresses, because though we test the concrete specimens under uniaxial stress in the laboratory, in the real life applications they are subjected to multi-axial stresses. So it is very important to understand and model their behavior under the multi-axial stress conditions. Then we also discussed the various failure theories for concrete under combined state of stresses. Then we looked into the concept of tension stiffening in concrete. So we'll start from the very basics, where concrete is it is made up of these different constituents. We have the cement, which provides the binding properties. Then we have the aggregates which provide the strength, and then we have water, which provides the binding property, and it's also important for the workability of concrete. Then we have different types of admixtures which help in enhancing the properties of both the fresh concrete as well as the hardened concrete. Then in multi-story structures we use high strength concrete, and as per IS 456, concrete having a strength of 65 to 100 megapascal is classified as high strength concrete. Then we looked into the concept of Abraham's law, which states that as the water to cement ratio reduces, the compressive strength of concrete increases. Then superplasticizers have been used to improve the workability of concrete. Then mineral admixtures such as the fly ash and silica fumes are added to concrete in order to improve the compressive strength. Then we looked at the lightweight concrete, and since the aggregates make up a significant weight of the concrete, by replacing the heavy aggregates with lightweight artificial aggregates, we can enhance the workability of concrete, and we can produce an efficient structural design, because it can significantly reduce the dead loads that are coming upon the structure. Then based on the ACI provisions, we looked into 3 categories of concrete depending on the densities that they possess. Further, we have the Indian standard codes and the ACI codes which are necessary to prepare concrete, lightweight concrete. Then we have some of the the chemical components that make up the cement, such as the lime, silica, alumina and iron oxide, and these are the 4 primary reactants, that is tricalcium silicate, dicalcium silicate, tricalcium aluminate and tetracalcium aluminoferrite. Those react with water in order to develop the CHS gels, which are responsible for the compressive strength of the strength of concrete. Then we have the hydraulic reaction, and then we looked into how an isolated cement particle, when it comes into contact with water, there is the process of hydration, and then there is hardening of concrete. Further, we looked into how the different reactants react with water in the process of development of the strength. So we have the different reactants. For example, we have the C3A and C3S, which are responsible for the high strength, and C2S and C4AF, which are responsible for the late strength. Then we have the different types of cement, which is classified essentially based on the compressive strength of the cement mortar cubes, and 53 grade concrete is the most prevalent and widely used concrete in the field. And then we also looked at certain special types of cement such as the hydrophobic cement, and then we have the sulfate resisting cement, which are used in special circumstances where the project requires us to use them. Further, we looked into the process of cement hydration, and then we looked how the capillary pores and gel pores are formed, and it is important to prevent the interconnectivity between capillary pores so that our concrete is not permeable, because a permeable concrete is highly vulnerable to corrosion because of the water that can seep in into the concrete, and the water can react with the steel rebars and result in the corrosion and subsequent strength degradation of reinforced concrete structures. So then we looked at some of the chemical shorthands. Then we looked into the process of hydration of cement. Okay. Further, we looked into what is known as the ettringite formation. So ettringite is a chemical that is a product of the hydration. So what we want is that the ettringite has to form at the earlier stages of hydration, because when there is a delayed formation, ettringites tend to have a needle-like structure. So that leads to expansion of concrete, and the expansion of concrete leads to the cracking within the structure of concrete, and this cracking again allows the water to seep into the concrete, and that leads to corrosion of steel, and then subsequently the strength and stiffness degradation of the structures. So then we looked at the evaluation of the mechanical properties. Firstly, we looked into the stress strain curves. So there we saw how that we need to test concrete cylinders in order to obtain the most realistic estimate of the stress strain behavior of concrete. However, for practical purposes, as per the IS codes, we have been using cubes of 150 mm size purely for the practicality, and however they need to be converted to the cylinder strength, and in order to truly understand their behavior in real structures. So then we looked at the mechanical properties between the concrete cube and the concrete cylinder. Then we looked at the variation in the compressive behavior when we change the grade of concrete. So as you can see from the stress strain behavior, the concrete which is having the least compressive strength has lesser peak strength, but it has a higher ultimate strain. So what we are trying to show in this slide is that as the compressive strength increases, the peak strain increases, however the ultimate strain decreases. Subsequently, the ductility of concrete, which is measured as the difference between the ultimate strain and the peak strain, that also reduces as we increase the grade of concrete. So we looked at an animation where the high strength concrete tends to develop a brittle failure. Then we looked at the mechanical properties of concrete that lies between the mechanical properties of hardened cement paste and the coarse aggregate. I hope all of you are with me. Hello.
Yes, sir. Yeah.
Yes,
Yes.
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 I've been talking for about 15 minutes, so I just wanted to make sure. So please feel free to interrupt in between, and so that we can have a discussion if need arises. Then we looked into the mechanical properties. So the IS code prescribes an ultimate strain of 0.0035 and a peak strain of 0.002, and then in order to calculate the stress corresponding to a given strain, because these are important for our numerical calculations. So the stress strain curve of normal strength concrete tends to follow this parabolic law, or the Hognestad stress strain curve. And similarly we have for the high strength concrete, since the stress strain behavior is quite different from the normal strength concrete, we have the Thornfeld stress strain curve, and this involves a little more involved calculations, where we have the factors n and k, where the factor n stands for it represents the variation of the slope as we move from the elastic to the non-elastic part, and the constant k represents the post peak strength degradation. So we will be solving some numericals based on the these two concepts later on in our interaction session today. And then we saw that as the rate of loading increases, the compressive strength of concrete also increases. Further, we looked into the characteristic strength, which we also looked into in our previous week, which is, it should not be more than the not more than 5% of the test results should be less than this value. So then we have again in order to evaluate the target mean strength, we have to use this expression where the target mean strength is given by the characteristic strength plus 1.65 times the standard deviation. So this standard deviation, as we looked into in the previous class, it is based on the IS code. So for different grades of concrete, we assume different values of standard deviation, and accordingly when we are preparing the concrete mix, we can prepare for a given target mean strength based on the grade of concrete required for the project. Further, we have the characteristic stress strain curve versus the design stress strain curve. So if we have the characteristic stress strain curve, we are using these factors. 0.85 corresponds to the size effect, and 0.8 corresponds to the conversion between the concrete cube strength and the concrete cylinder strength. And then in order to develop the design curve, we are designing it further by a partial safety factor of 1.5 that leads us to the design compressive stress of 0.447 FCK. So if we are considering concrete of M30, so the design compressive stress is merely 0.447 times the value of 30. So moving forward, we have the tensile strength. Again, the dog bone specimen, it is quite difficult to test, so we find there are indirect methods of estimating the tensile strength. First, we have the flexural test in order to develop the modulus of rupture, that is given by 0.7 root FCK. Further, we have the splitting tensile test of concrete cylinders, and then based on the load at which it fails, we determine the tensile strength based on this equation. Indirectly, we can also obtain the tensile strength of concrete based on the failure load of the concrete cylinder under compression. So here F prime C, that variable denotes the compressive stress at which a concrete cylinder fails. Moving forward, we looked into the concept of tension stiffening. We also have a question on this now. So essentially what it represents is that at the location of crack, So the loads are entirely taken up by the reinforcing steel. However, in between the cracks, concrete takes up a part of the tension because of the bond that is existing between concrete and reinforcing steel. So we have a stiffening effect uh, because of the as the concrete comes into the picture in resisting the tensile loads. So further we looked into the behavior of concrete under multi-axial stresses. So we have a case of triaxial state of stress consisting of the axial load and lateral confining stresses along the two orthogonal directions, as you can see in this plan view. And as the confinement increases, we can see that the ultimate stress and strain of concrete also increases. So this is a very nice representation of depicting how the behavior of concrete changes when going from biaxial to uniaxial loading. So as you can see, this is a uniaxial compression test, and this is the biaxial compression test. This represents the uniaxial tension test, and this represents the biaxial tension test. So we looked into the different failure theories. So for ductile materials, we have the Tresca and von Mises yield criteria, which represents the behavior of ductile and metallic substances. However, since concrete is a brittle or a quasi-brittle material, so the modification of Tresca criterion has been adopted as Mohr-Coulomb criterion, and a generalized version of the von Mises criterion is adopted as the Drucker-Prager criterion. These are the failure envelopes. So this was the first part of the module. Then we will go ahead with the second part.
Excuse me, sir.
Yes.
I have question regarding the first part of this module. Regarding the
Yes, please go ahead.
hydration,
Yes.
yeah, regarding hydration of cement, I
Yes.
want to know about what is the effect of temperature on hydration of cement. And as a designer, what should we be aware of while designing the structure that is located in the heavy snow area where the
Okay.
mass concreting is going to happen during the winter season.
Okay. Okay. So if it is in a heavily snowing area, curing of concrete becomes difficult because it is important to maintain a certain temperature. As you know that sub-zero temperatures water exists as ice, and at higher temperatures it is not desirable. So we can look at alternative methods, such as we have the precast construction. uh, are you aware of the precast construction?
Yes, sir.
Yes, so precast construction is where the structural components such as beams and walls, they can be casted in a controlled environment. Uh, so that is one way of tackling the problem of extreme temperatures.
Yes, sir.
Yeah, yeah. So quickly we will go through the the second part of the module, which corresponds to the long-term properties of concrete. So in the initial part, we looked into the stress-strain relationship of concrete as per IRC 112, based on which the bridges are designed. Then we looked into the concept of creep and the factors affecting it. Then looked into the effect of creep on the structural behavior. Then we looked into the shrinkage and its types, and the effect of temperature on the material and structural behavior. So these are essentially the properties. I would recommend that you look into the codes, because I think me going into the specifics will not be much productive for you right now. However, I would like you to pay attention to the different properties that have been identified, and we will be looking at some of these properties in the questions that I framed also. So as we saw previously, the stress strain curve tends to follow a parabolic profile. It can be approximated into a triangular profile for ease of calculations. Okay, so these are as you can see, this is a very interesting chart which shows what would be the strain that is induced in the concrete elements along with the passage of time. So this below the axis it corresponds to expansion, and above it corresponds to the contraction. So when we are casting the concrete and we begin to cure them, we see what is the swelling because of the curing process. However, there is the process of autogenous shrinkage, which corresponds to the shrinkage that is resulting out of the chemical reactions that is occurring in concrete. So this corresponds to the autogenous shrinkage. Then we have the drying shrinkage due to the temperature effects, and this point T corresponds to the point of loading of the structure. So once the load starts to act on the structure, there are strains due to the creep. So we have the creep due to loading. So we will be discussing more about in a question in a few minutes. Then we have the properties, long-term properties. Then creep is essentially defined as the deflection that is being caused in the structure due to the application of loads for a long period of time, that is load that is being sustained over a period of time. So the first component is called the elastic deformation, that is caused due to the loading, but when it is sustained over a period of time, we have the phenomenon of creep. Okay, so we have the progress of creep with time. So then we have some of the properties which are affecting creep. So here we see that the steam curing helps us in reducing the creep. Then the high strength concrete, which is generally associated with a low water cement ratio, has a lower creep. Further, creep is facilitated with higher temperatures. Further, when there is high humidity in the environment, there is already a sufficient water vapor in the environment, so there is less creep. Then we see that the high content of cement paste also associated with high amount of creep. So we use the following expression based on the IS code in order to evaluate the effective modulus of elasticity. So the creep induces deflections, as we saw earlier. So we have this clause 6.2.5.1 based on IS 456. So based on the different periods of the age of concrete, we can factor the effect of creep based on this creep coefficient, and using this modulus of elasticity, we can determine the deflections accordingly. Moving forward, we have shrinkage. Shrinkage is defined as the reduction in the volume of concrete because of the loss of moisture, and here we see that whenever there are restraints, it tends to form cracks because of the change in volume. then if there are no restraints, however, there is no issue of cracking. So similar to the creep, we factor into the design the shrinkage strain. Further, we have different types of shrinkage. We have the drying shrinkage, we have the autogenous shrinkage, and we also have what is known as the carbonation shrinkage, which involves the interaction of the products of hydration along with the carbon dioxide present in the atmosphere, that ultimately leads to shrinkage in the concrete. So these are the different parameters which affect the process of shrinkage. So as we can see, a specimen that is stored in water does not undergo shrinkage. However, when it is subjected to air, depending on the moisture, on the temperature, the shrinkage can vary. Then it is very important to perform the curing of concrete in order to avoid the process of shrinkage. So as we can see, this is the comparison between the specimens with no water curing and curing for 7 days and so on. Then the temperature for the curing is also important and plays an important role in the subsequent shrinkage of concrete. Then we have some more properties which are responsible for the drying shrinkage, such as the reinforcement, then the volume to surface ratio. We will be solving some problems based on this. Then we have the plastic shrinkage, which occurs in the fresh state of concrete. Then you have the carbonation shrinkage. Moving forward, we'll look into the third part of the module. I hope the screen is visible.
Yes, sir.
Yes.
Yes.
Yes. So we will try to wrap up as soon as possible because we have around 20 questions. So we'll be starting the MCQs very shortly. So in this part of the module, we look into the tensile properties of reinforcing steel, the different types of reinforcing bars, then the advantages of and disadvantages of steel and FRP rebars, then the different grades of steel rebars, followed by the stress strain behavior of steel and FRP rebars. So as we have seen earlier, the compressive strength of concrete is approximately 10% of the tensile strength is approximately 10% of the compressive strength, which is why the requirement of reinforcement arises. So we have the different grades of concrete. We have the mild steel bars, which is of Fe250 grade. We have the high strength deformation, or the HYSD bars, which are of these different grades, and the letter D stands for ductile, because whenever we are using steel in seismic areas, we need to design the structural members to behave in a ductile manner. So ductile behavior of steel is essential to safeguard structures during earthquakes and seismic loading conditions. So the IS 1786 is the governing code for the reinforcing steel. Then we have the cold twisted bars and the deformed bars. Then we have the thermomechanically treated bars, which results in involves the following 3 steps of heat treatment, and it consists of a tough outer core and a soft inner core, and the strength is essentially an outcome of the ferrite perlite structure that is being formed due to the process of treatment. So it is deformed into different configurations in order to ensure a better bond with the surrounding concrete. Then we have the stress strain behavior, similar to what we saw in concrete. As the grade of steel increases, yes, the ultimate strain is reducing. Okay, moving forward, we have, again, as we looked at the the difference between the characteristic strength and the design strength of concrete. Usually we use a partial safety factor of 1.5 for concrete. However, for steel, since it is based on a very manufacturing in a controlled environment, we use a lower factor of safety, which is 1.15. So it is usually reduced by a factor of just 1.15, the design stress. Moving forward, again, these are the specifications and the minimum elongations that are required for different grades of steel rebars, because as we saw, as we increase the grade of steel, the ultimate strain and the ductility tends to reduce. So in order to ensure the ductile behavior, it is very important that the steel that is being used has the following minimum elongation. Okay, so moving forward, this is the stress strain curve based on the IRC code. So one of the major drawbacks of steel reinforcement is that it is highly susceptible to corrosion. Whenever there is moisture, it tends to react with the OH ions in order to form the rust and other products of corrosion, which leads to the strength degradation over a period of time. So it is very essential to ensure that the concrete that we are preparing is impervious to the water. So in order to avoid the problem of corrosion, we have introduced the galvanized steel, and we have the epoxy coated steel, which can prevent the process of corrosion in case there is ingress of water. Then we also have the FRP rebars, which have excellent strength to weight ratio. So these are embedded in matrices, and they provide excellent strength, almost comparable to that and even higher than that of the reinforcing steel. So there are different types of FRP rebars, such as the glass rebars, carbon rebars, basalt and aramid rebars. Then these are some of the mechanical properties. However, the major issue is that the stiffness is quite lesser when compared to the steel rebars, and they do not show a ductile behavior, because the reinforcing steel and the pre-stressing steel, before the failure, they give us adequate warning in the form of high elongations. But for the FRP bars, it just reaches its ultimate load and then ruptures. So it is important to design with considerable care and caution, and also the stiffness is lesser when compared to the rebars, the steel rebars. Okay, so this with this I will conclude the summary of this lecture slides. So I welcome any questions if there are any. Yes. So the reason why I took up the discussion of the summary is because the week 2 lecture was quite involved, and it included lot of content. So I just wanted to refresh the memory so that we will be in a better position in order to attempt the multiple choice questions. So if nobody has any further questions, we can go ahead with the MCQs. I look forward to interacting with you all, and let's make it interacting and engaging session. I hope my screen is visible now.
Yes.
Okay. Okay, so the first question is, the correct arrangement of reactants in cement in terms of the rate of strength gain in the ascending order. That is, first we have to place with the reactant with the least rate of strength gain. So moving forward, the highest rate of strength gain. So out of these four options, what would the right answer be?
C, sir.
I'm sorry.
Hello.
Can you repeat,
C,
please?
C.
Okay.
C for Calcutta.
Okay. Okay.
A. Option A.
Okay. So when you're looking at these options, I would also like you to look into these symbols as well. So it means that, for example, for option B, it means that C2S is less than C4AF. So it represents that C2S has the lowest strength, rate of strength gain, and C3A has the highest rate of strength gain. So if there is no other answers, I would like to go ahead. So the correct option is B. So as we saw in the lecture slides, the compounds C3A and C3S, which are represented by the square and triangular markers, they attain strength quite early. So they are responsible for the early strength formation, whereas the compounds such as C2S and C4AF. So C2S is represented by the diamond markers, and the C4AF is represented by the circular markers. So these are responsible for the lower rate of the late strength gain. So the correct option was B. So I hope the slide is visible to all of you and the contents are visible.
Yes.
Okay. So we will move on to the next question. So we looked into the process of delayed ettringite formation in concrete. So which of the following statements are true about this process?
One option is C, that is true.
Okay. So we just to clarify, we are looking at the right options, right? True statements. Okay. So to give you a hint, there are two statements which are correct.
Option C and E.
Okay. Okay. Anybody else would like to volunteer? Anybody else would like to answer? So as the participants said,
C and D, sir.
yes, option C and D are the right options. So may I know who gave the answers?
Uh,
Okay,
one was given by me, Vikram.
right. Okay, thank you.
Second was by me.
Yes, thank you for the answers. Yes. So Ettringite is I will forward this link of this research article, which helps you to better understand the Ettringite formation. It's a major issue, one of the major issues with respect to concrete. I am sure if you're working in the industry, you might be having some experience with the cracking, and the cracking is attributed to the process of the delayed Ettringite formation in concrete, which is why the topic is of considerable interest in the research as well. So as we can see, when there is hydration of cement in concrete, it leads to the formation of Ettringite, which is essentially this compound. However, when there is high heat, there is the Ettringite is becomes unstable, and it tends to form this calcium monosulfur aluminate, and later when moisture and sulfate becomes available, the calcium monosulfur aluminate tends to convert back into Ettringite, and this Ettringite, as you can see from this microscopic image, it is a needle-like structure, and it leads to significant expansion within concrete, and the concrete the expansion leads to the formation of cracks. So which is why this the process of delayed Ettringite formation is highly undesirable, and the statement 1 is incorrect because it is a needle-like crystalline structure. Then high early heat accelerates the process of Ettringite formation. Then so we need to maintain a curing temperature of 65 degree and below, in order to avoid this phenomenon, and the options, the statement C and D are absolutely right. So moving forward, we have question number 3. Which of these statements are true regarding the stress strain curve of concrete cylinders of different grades?
Mhm. Option B.
Option D, is it? D for Delhi?
Option
Yes.
mm,
D.
Okay. Thank you for your answers. So, as some of you have pointed out, let's move forward. As you mentioned, the correct answer is option B. So, let us look at the explanation. So, excuse me. So as we can see, we can see that the concrete cylinders are having different strengths. So the stress strain curve represents concretes of higher and higher grades. So as the grade of concrete increases or the compressive strength increases, we see that the peak strain is also increasing. Okay, I hope you can identify. The peak strain is denoted by this dotted line. So as the strength of concrete increases, the peak strain is increasing. However, the ultimate strain, it is reducing. Okay, so that is what we are trying to capture in this slide also. So with increasing the compressive strength, the peak strain is increasing. However, the ultimate strain is decreasing. And ductility is essentially the difference between the peak strain, the ultimate strain and the peak strain. So as you can see, for the concrete of lowest strength, the ductility is quite high. However, as we go on increasing the grade of concrete, ductility reduces. So as the grade of concrete increases, the ultimate strain also reduces, and also the ductility reduces. Moving forward, for a concrete having a peak cylinder strength of 30 MPa, that is F prime C, determine the stress Fc corresponding to a strain of 0.0015. Assume the peak strain of concrete as 0.002. So as some of you were asking in the previous class, I have prepared a numerical, and I hope we can solve the problem together. But first I would request all of you to try the problem first, and if there is any hint, I'll be happy to provide. So let's take 2 to 3 minutes. Okay, all of you try to attend the problem and suggest the answers. So basically there are two stress strain relations for concrete, that is the Hognestad relation and the Thornfeld relation. So which of those relations do you think will be applicable for this particular problem?
This first one,
First is
Afghanistan.
Yes,
Hognestad.
yes, absolutely right. So yeah, please go ahead and let us know the answers.
Option E, 28.125.
Okay, so one of the participants has answered that option E is the right answer. All of you try the problem and let me know. Anybody else got the answer?
E 28.125.
Okay, thank you for your response. Anybody else would like to volunteer? Yes. So before going further, I would like to confirm from all of you. I hope you're able to download the lecture PDF from the website. Participants?
Yes, we are able to download.
Okay. So just like I showed in the summary, I recommend that all of you can highlight them and make use of them. Okay.
So actually lecture is given for this month, part 3. We have got only presentation only. Is it presentation only we are able to download?
No. I meant Professor Surya Prakash, his whatever he's teaching on the portal.
Yeah.
Those slides, I think you are able to access.
That I are able to access, sir. But no
Okay.
lecture is there. Lecture part is there. Some transcript part is there. That is not available.
Okay. So, you can contact the NPTEL, or you can email me later. I'll be able to arrange that for you.
Okay, thank you.
Yes, thank you. So, right. So the correct answer is E. Okay. So for some reason, I will go to the PowerPoint presentation, because, excuse me, let me just close this. Yes, so I think we were in problem number 4. Okay, so allow me to use this. So actually the equation is quite straightforward. Yes, so we have, excuse me, it is showing some interference, which just why it is extremely difficult sometimes. Apologize for the convenience. So we have the fc by fc prime is equal to 2 times epsilon c. I hope all of you can see my writing.
Yes, sir.
Yes.
Yes, thank you. So it is quite straightforward. So what we need to do here is epsilon prime c square. So we know that the compressive strength of cylinder is 30. Substitute the value of f prime c as 30 megapascal. Then we have given the value of epsilon prime c, that is the peak strain, as 0.002. Then again epsilon prime c, you have epsilon c here becomes 0.0015 because we are determining the value of fc corresponding to a strain of 0.0015. okay, so when you plug the values in this particular equation, we get option D, that is option D, that is 28.125. okay, I hope it is clear. Yes.
Yes, sir.
Yes, okay. So moving on, we will go to the next question. Okay. For the concrete that is mentioned in question 4, what would be the modulus of elasticity? This is quite straightforward. You can take 2 minutes for this question.
So please repeat question 4.
I hope you can see the screen. I hope the screen is visible.
Question 4 I was. Question 4.
So question 4 we just, okay, just for the data, I'll help you with the data. Yes. So this is the data.
Okay.
Concrete cylinder strength is 30 MPa, and that is the only data that you require for the to determine the modulus of elasticity.
Hmm. $27,386.
Right. 27,000.
So 27,386 it is.
Okay, so does that come in any one of the options here?
So
So near to see.
near to C.
Okay, okay.
D option.
Okay, thank you. Keep the answers coming.
30,408.
So it's 30,000, somewhere around 30,600.
Okay. Okay. Yes, anybody else is trying to solve the question? If not, I will go ahead with the answer in the discussion. Okay, so the correct answer is option D. Okay, so I think there is a mistake. The correct answer has to be option C. Okay, so we will solve the problem now. So I think one or two of you had answered option C. Option C is the right answer. So let us look at how we are going to solve it, right? Okay, so so if there is any doubt, we can solve it over here, right? Okay, so we saw that f prime c is given as 30 MPa, and what would be the modulus of elasticity of concrete? What is the equation?
Hydrogen square root FCK.
Yes, so it all comes down to finding out the value of FCK. So we have seen in the one of the lecture that this is basically the cylinder strength. So what we need to determine the value of FCK is the cube strength. So that is represented by FCU, and that is given by 30, that is f prime c into 1.25. Okay, all of you are with me? So this gives a value of 37.25, right? Moving forward, based on the IS code, we saw in the last week discussion that the characteristic strength FCK is given by f prime ck or FCU. In the code it is given as f prime ck minus 1.65 sigma. So here f prime ck corresponds to the target mean strength. So target mean strength corresponds to 37.25 minus 1.65 sigma, and for when we assume the value of 5 sigma, standard deviation of 5, we obtain the value of 29.25. Okay, so when you plug the value in this particular equation, Okay, we get the value of 27041.6 MPa. I hope the explanation is clear. And this particular sigma has to be taken as 5. It is based on I think IS 10262. (2019). I hope the explanation is clear.
So, can I ask a doubt?
Yes, please go ahead.
Yeah, whenever we test the cubes
Yes,
on sides, the strength what we get is FCU. So we have to arrive at FCK to cross check with the adapted design strength in our designs.
yes. Actually, last week also we were having this discussion. So whenever I think if you're asking from an industry perspective, let's
Yeah.
say that for the project they have prescribed that we use M30 concrete, right?
Yes.
So when the concreting is being done, for the quality control, simultaneously we are going to cast a given number of cubes. And when we perform the compressive strength of those cubes, so that has to conform to this particular value, this f prime ck. So let's say that you're using M30 concrete, so f prime ck, that has to be fck plus 1.65 into sigma. So this sigma, it can be 4 or 5 or 6 depending on the grade of concrete, but for M30 it is 5. So it is we can calculate it actually, like that would be 30 plus 1.65 into 5. So can anybody volunteer what would this value be?
38.25.
Yes, so the value has to be 38.25. So whenever you are testing the concrete cubes, it should not go below this particular value.
Now, what about acceptance criteria?
Yes, you mean the material acceptance, right?
Concrete acceptance criteria.
Yes,
And some will fall above this, some will fall above below this.
Okay, so I don't know the exact figures, but as far as possible, since we are defining the characteristic strength as 5% should not fall below this. So we have to look into the codes actually, but as far as possible, I think we need to aim for a compressive strength of 38.25 or above that.
Okay.
Yes.
Yeah, thank you.
Yeah, thank you. Thank you for the question.
Hello, sir.
Hello.
Okay, so can we conclude that if your cube strengths are more than 38.25, then only you have achieved the characteristic strength of 30 MPa?
Yes, because that is one aspect. I mean, when it comes to concrete, there are different parameters, but at least when it comes to the strength, if we are able to achieve 38.25, so we are adhering to the codal guidelines, and that qualifies as an M30 concrete. But if you are casting multiple cubes and if they are falling below this particular compressive strength, then I don't think it will qualify as a M30 concrete.
Okay.
Yes, so it is very important that a significantly high number of cubes that are tested have this minimum amount of compressive strength.
So basically, on the field, the concreting agency, what they do, RMC people,
Yes.
they cast their cubes, and suppose we have ordered M30 grade concrete,
Yes.
and if the test results are more than 30, like 32, 35 MPa,
Yes.
so should we accept those results?
uh, Strictly going by the code, we should expect that the strength will be above 38, because all our design calculations, right? Because obviously as a design engineer you will feel concerned, right? Because
Yes.
you would have asked for M30 concrete, and we are taking lot of partial safety factor. So I think from the design point of view, and also from the durability, I think it is important that they meet this compressive strength.
Okay.
Yes.
Okay. Thank you.
Yeah, thank you.
So, but just like interacting with you with some other interactions,
Yes.
at least what I concluded was this 1.65 times standard deviation is considered only for target strength.
Yeah,
And if you get
exactly.
the cube
Yeah.
strength even at around 30, it
Okay.
should be satisfactory.
uh, okay, but
Because in my experience, because even if you go for M30, you never find any test results coming somewhere on 38 and all.
okay. Okay, right, sir. So uh, yeah, may I know who asked the question?
Myself,
Okay,
Vidyadhar.
okay. So I think like the codal provisions, they are there for a reason. I mean, I don't mean to discourage that, but I think as far as possible we should try to adhere to the standards, because as we have seen in the previous lecture, the characteristic strength, they have certain meaning, and we should have very tolerance when it comes to any lesser strength. That is my personal belief, because I am also consulting in some projects, and we expect that they deliver on that particular quality.
Okay.
Yes.
So it
All right,
should be
thank you.
strictly around 30. It
Yeah,
should be strictly 30 M30 grade.
yeah, as far as possible, and again, that is desirable.
Means that
Yes.
means we are saying that whatever the cubes we have tested, they have meet the target strength. Then only we can accept those results.
Yes, yes, that is true. Yeah.
Okay, so we need target strength, not FCK.
Yeah, FCK is used for the design purposes, but when we are testing, they should be able to meet the target strength.
Okay.
Yeah, can I add something to this? Because
Yes, yes, yeah, please go
yeah,
ahead.
uh, yeah. Regarding the cube strength testing, now
Yes.
basically in IS 456 there are two clauses
Yes.
which clearly mentions what is the requirement for acceptance criteria. Basically, in cube testing there are two parameters which are checked. One is the average cube strength, that is for
Yes.
one set of cube that consists
Okay.
of three specimens,
Mm-hmm.
and for individual also there is a requirement of minimum compressive strength that is there. And this requirement for additional strength, one considering the standard deviation value, that is also there. I mean, it is clearly mentioned in the IS 456. One can go through that and check the details. So basically, three criteria are there, as you
Yes.
mentioned. FCK plus some standard deviation value, plus average of three cube specimens, and individual cube strength also, I think.
Yes, yes, yeah.
You can check that.
Thank
Yeah.
you for your inputs. Again, we have to look into the individual specimen and also multiple specimen, because as you increase the sample size, I think the confidence increases, because you cannot determine based on one cube test only, which is why we take numerous samples. Right. So I think we can move ahead. Okay, so we have a lot of ground to cover. We have 30 minutes and we have 15 questions, so yes. Okay, so we have another numerical question, and this is based on the Thornfield equation, just to save you time. So I suggest you to calculate and let me know the answer for this particular question. So for a peak cylinder strength of 60 MPa and corresponding to a strain of 0.001, what would be the corresponding stress? So again, the hint is kindly use the Thornfield relation in order to determine the value of stress Fc. Okay, any one of you got the answer? Anybody? Anybody is trying? Should I wait for 1 minute? Okay, so let me just go ahead with the answer. So the correct answer is D. We have to use the Thornfield relation for the higher grade of concrete. So let me just open up the PowerPoint presentation. Right, so we need to find out, so there is a correction in this equation, which is why I took up this problem. I hope my screen is visible. Yes. So here in this particular equation, we need to consider FCU. Okay, and here also we need to consider the value as FCU, not FCK. So that is going to change the calculations a little bit. Okay, so we can start the problem. So firstly, we have the strength of cylinder, that is F prime C, as 60 MPa, So into 1.25 gives us the value of FCU. So FCU becomes 80, I'm sorry, I think it is 75 MPa. So that would be 75 MPa. Then we have to plug it in the equation for N. N is given by 0.8 plus FCU by 21.25. So from this we have the value of plugging 75 MPa here, you get the value of 4.33. Moving forward, we have to find out the value of modulus of elasticity, that is EC. EC is given by WC power. WC is the density of concrete, so it is 2400 power 1.5 to 0.0385 into that is again square root of FCU. So this will give us the value of 39202 megapascal. Okay, moving forward, I think we have the value of N and K for when the value of stress is less than 0.002, so that would be 1. Okay, and epsilon prime C I calculated, and yes, epsilon prime C you can calculate just to ascertain yourself. So that would be 0.8 FCU by EC into N over N minus 1. So you can substitute all the values and obtain as 0.002. Okay, ultimately we have all the values. We have the value of N, we have the value of K, we have the value of epsilon prime C. We have, by using the value of epsilon C as 0.001, okay, for epsilon C is equal to 0.001, you get a value of FC is equal to FC would be 38.44 MPa. And what would be the value of F prime C? Anybody? It is the cylinder strength, nothing but 60 MPa given in the question. Okay, so this is how you develop the answer, arrive at the answer. Okay, so moving forward, please interrupt me if there are any questions. We can take a bit extra if extra time if you are not able to complete. So since this was a large module, I framed number of questions. So again, I would like to highlight that the main objective of framing this interaction session is 2 points. First point is that it will help you to revise all the concepts, and it will help you to apply the numerical problems. I hope you're gaining something out of this session. So we can go forward. So the modulus of elasticity we have calculated. It is anybody noted down the value of modulus of elasticity? Hello?
38.44 you done.
Sorry, which option?
38.44 you got the answer.
Oh, that was the value of FC. So that was the value of
Okay.
FC. Yeah, and modulus
Okay,
of
okay.
elasticity, that was? So the modulus of elasticity was option C, 39202. Okay, so using this equation we obtained the value of modulus of elasticity. Okay, another simple straightforward question. We already discussed this in the class earlier today. Anybody would like to refresh, answer the question?
Option D, 38.5.
Yes, that's absolutely right. Okay. Okay, moving to the next question. So in the previous question, we saw what would be the target mean strength. Now for M40 concrete, what is the design compressive strength? That is the compressive strength that is considered for the design.
A.
Okay. Anybody else?
Option A.
Okay. Anybody?
Yes.
Okay, okay. So it is quite straightforward. So the answer is A, and as we can see, this is taken from IS 456 page 69, and it is quite straightforward. This is the characteristic strength. We are going to reduce this by a factor of 0.67. So the factor of 0.67 comes from the one of the earlier slides we had discussed that 0.8 into 0.85. This gives us 0.67. Then when you again divide that by the partial safety factor, we obtain the value of 0.447. 0.447 into 40 gives us the value of 17.87. Okay, moving forward. So again we have a numerical. M40 concrete prism of 100 mm square cross section is subjected to 4-point bending stress. If the maximum bending moment at the failure is 1 kilonewton meter, what is the corresponding flexural stress? Compare it with the modulus of rupture. You can take 2 minutes. So at this point I would like to ask the participants, if there is no pressing commitments, can we extend the class by 15 minutes?
Yes, sir, definitely.
Okay, okay.
Okay.
Yeah, thank you. So we will conclude at around 9:15 p.m. IST. So may I know what is the local time at Japan right now?
It's 12, 16.
Okay, okay. I hope it's not an inconvenience.
It's completely fine.
Okay, okay, great. It is nice to have participation from last week from Africa. Also, one of the participants had joined.
That's great.
Yes, thank you.
Option D.
Okay, thank you for the response.
Option D.
Sanjeev.
Okay. Okay, so as most of you pointed out, the correct answer is option D. So they are given by these values, these expressions, that is 6m by bd square, that is m by z, m by section modulus, and the modulus of rupture is given by 0.72 FCK. So do you want me to expand this equation, or we can move ahead?
So move it.
Okay, okay, okay. Anyone is not following, kindly feel free to interrupt. Okay. Okay. Identify the incorrect statement with respect to the concept of tension stiffening in reinforced concrete. Anybody, can you identify the incorrect statement among these four options?
Yeah. Option A.
Okay. Anybody else?
And option D.
Okay. Okay. Anybody else would like to volunteer?
C option.
Right. Right. So among the options, the correct option is option C. I made the question little technical and long in order to confuse you, but yes. So the explanation is that when a reinforced concrete member cracks, so these are the cracks, and at the location of the cracks, the tensile load is entirely resisted by the steel rebar. However, in between the crack, the concrete also resists a part of this tensile load, as a result of which the reinforcement, the stresses in the reinforcement and the strains, they decrease. Okay, so the reinforcement strain at the uncracked zone is less than the strain at the cracked zone. Okay, so the rest of the options are correct. The concrete acts in tension between the cracks, and in between the cracks a part of the loads are resisted by the concrete, and it leads to a decrease in the reinforcement strains and stresses, and an adequate bond between the steel rebars and the concrete leads to a stiffer load deformation response. So this is what we are looking at. So this is the location where this the concrete member is cracked, and this is the stiffening effect that is provided by the concrete between the uncracked between the cracks and the uncracked region. So the next question: chronologically arrange the following components of shrinkage and creep within concrete during the service life of a structure.
See, sir. CMDR said
Option C, sir.
Okay,
I think it is option A.
okay.
B and D, sir. B and D are same which is given.
Oh, okay, okay. I think there is, yeah, there is a small mistake. I think, yeah, B and D are the same. So you can still answer. You can choose between A, B, and
So
C.
B and D, sir. B and D.
Okay, okay. Yeah, so the correct answer is, as you pointed out, it is B and D, because as soon as there is once the hydration starts happening, there is autogenous shrinkage because of the reaction between the chemical components and the water. Then there is drying shrinkage followed by the load induced strains followed by the creep strains, because the creep strains are because of the sustained loading over a long period of time. Okay, moving to the next question. Identify the correct statement with respect to the concepts of creep and shrinkage. Here you can select multiple options if necessary.
Sir, can you show the previous graph once again?
Yes, yes.
Thank you.
So this is available in the lecture slides. You can go back to the long-term properties, the lecture on long-term properties, for better clarity. So initially there is autogenous shrinkage, that is because of the process of hydration. Followed by that we have the drying shrinkage because of the drying of concrete structural members. Then this point T corresponds to the point of load application. So then you have this initial strain, that is load induced strain. Then we have the creep induced strains. So we have the basic creep, then we have the drying creep. Okay, so the stresses is a combination of initial loads and then the creep loads.
Thank you.
Yes, I hope we can move forward.
Yes.
Yeah, so select the correct options corresponding to the concepts of creep and shrinkage.
A, B, and D.
Okay,
A, C, and D.
Okay, okay. I would request all of you to.
I think it is option A, B, and D.
Okay. So all of you, I request you once again to look at the options, read them carefully. Okay, we'll go to the answer. So the correct answer is only option A. So I think there was some confusion. So the explanation is that option B is incorrect. Option A is correct because it is referred to as the long-term deformation caused by application of loads during a long period of time under sustained loading. Option C is incorrect because it can be reversed because there is a component of elastic recovery upon the removal of loads. Option C is incorrect because shrinkage refers to a decrease in volume, not the increase in volume. And ultimately, the factors that are responsible for creep are same or largely similar for shrinkage also, because there also, because of the moisture content, the creep and shrinkage, they largely depend on similar factors. Okay, I would urge all of you to go back to the presentation slides and just look into the concepts of creep and shrinkage once again. Okay, so for M30 concrete, what would be the effective elastic modulus for a period of 28 days and 1 year? So the hint is, first you have to determine the elastic modulus for 0 days. What would be the elastic modulus given by 5000 root FCK? Then you have to take the corresponding creep coefficients, arrive at the value of effective elastic moduli for 28 days and 1 year.
Option A.
Okay. Anybody else would like to answer? Anybody else is trying? So I think we can go straight away. So the correct answer is option A. Thanks for the answer. So yeah, we have the for different age of concrete, we have different creep coefficient. For 7 days it is 2.2, for 28 days it is 1.6, and 1 year it is 1.1. And then first we have to determine the value of modulus of elasticity. Let me quickly do that for you. Okay, so we have the modulus of elasticity as EC is equal to 5000 root FCK. When we have to find out the effective modulus of elasticity, quite simple. Use the value of EC, then 1 plus 1.6 for 28 days strength. Okay, and for 1 year replace the value of 1.6 by 1.5. Okay, I think we can move forward. Okay, moving forward, identify the correct statement with respect to shrinkage in concrete. Anybody would like to volunteer?
D option.
Okay, thank you for the answer.
I think it is option D, last one.
Okay, okay. Okay, so the correct answer is, as the two of the participants pointed out, it is option D, because according to option A, the shrinkage is independent of the external stress conditions in concrete, and shrinkage is reversible and depends on the moisture content available in the environment. Then concrete structural elements with low surface area to volume ratio experience low levels of shrinkage. Okay, and the option D is the right statement, because the types of aggregates and admixtures that are used in concrete influence the shrinkage within the concrete. Moving forward, which of the following statements is incorrect about the carbonation shrinkage? So we have to identify the incorrect statement. Okay,
Sir, option C.
okay, okay. So can you volunteer and tell what should be the correct statement in option C? What should be the correction? Option C is the correct answer.
I think all are correct, sir.
The high pH, I think.
Yeah, exactly, exactly. So the correct option is Okay. I think there is a mistake. I think the answer has to be option C. Because yeah, I mean, I'll check it and get back to you. But as far as my memory goes, formation of calcium carbonate results in the lowering of pH of concrete, and higher pH is associated with the protective oxide film, because when you reduce the pH, there won't be any protective film any longer. So the incorrect statement is C. Okay, and the remaining options are right. So carbonation shrinkage occurs when the calcium hydroxide in the fresh concretes reacts with the carbon dioxide, leading to the formation of calcium carbonate and water. So this lower pH is detrimental to the oxide film that is present around reinforcing bars, and once the oxide film is gone, then it becomes vulnerable to corrosion. So option C is the correct answer. Okay, so we had solved a similar problem last week also. So what are the yield strengths of mild steel bars and HYSD bars? And the yield strength we are determining corresponding to a stress of 0.87 Fy. So you can take 2 minutes. I hope some of you are trying. So I wanted a quick feedback. Would you prefer that we take a break after 1 hour, or is the present format fine?
So let's continue.
Okay. No, I meant for the subsequent classes that since we are here for more than 2 hours, some of them might prefer that we take a 5 minutes break after 1 hour, so that we can come back fresh. So
Option A.
okay, thanks for the answer. So we can discuss the modalities next week. Yeah.
Option A.
Okay. Okay, so just to give you a hint, for HYSD bars, we're using the concept of 0.2% proof stress. Okay, so it is not straightforward. So we have to add something. So we can go ahead with the answer. So the correct answer is option B, because as I've mentioned over here, have I provided the, yeah, here it is. So you can look here, the yield strain is given by 0.87 Fy by Es, substituting Fy as 250 MPa. Okay, so substituting the value as 250 MPa. However, for Fi 415, it is given by this particular equation. Okay, so the reason is, as we can see, there is a clear plateau and there is a distinct yield point for mild steel. But for the HYSD bars, there is no distinct yield point. So there is a gradual curve, because of which we need to consider the 0.2% proof stress. So when you draw the when you consider the strain of 0.002 or 0.2%, and then when you draw a line that is perpendicular to the initial stiffness, okay, so it is also called as the offset method. So when you draw this, the point of intersection, so this is basically the value of yield strain, okay. So this turns out to be 0.87 Fy by ES, and this is wrong. This has to be point plus 0.002. So when you do the calculation, it comes out to be 0.0038 as opposed to 0.0011 for 250. I hope it is clear. Right, moving forward. As per the Indian standards IS 13920, the minimum elongation of steel bars required in seismic zones 3, 4 and 5 is anybody would like to volunteer? It is factual, it is taken directly from the lecture slides. Okay, so the correct answer is C. Oh, I'm sorry, I think there is a mistake. It has to be option D. It is 14.5%. Okay. So as per IS 13920, steel bars in seismic zones 3, 4 and 5 have to have a minimum elongation of 14.5%. Okay, moving forward. Okay, so based on the decreasing value of modulus of elasticity, arrange the following rebars. So we have the pre-stressing steel, we have the carbon FRP, we have the steel reinforcing steel, we have the glass FRP, and finally we have the aramid FRP. Anybody would like to volunteer?
Option D.
Okay, thank you for your response. Anybody else would like to answer?
Option B.
B. Okay. So we are looking at the decreasing value of the modulus of elasticity.
I have a doubt here. Actually, frequently modulus is less than steel. No?
Okay, so we can discuss after the solution.
Okay.
Yes. So let's proceed quickly. So the correct answer is option D. So pre-stressing steel is considered equal to be steel, and then followed by CFRP, AFRP and GFRP. So coming to your question, so steel as a material, we consider that the Young's modulus is same irrespective of the different types of steel that we have, whether it is pre-stressing steel or the normal reinforcing steel. Even for the mild steel bars and the HYSD bars, or even the stainless steel that we use for the utensils and building the ship vessels. So theoretically it is considered as the same. I hope that answers.
But it is given. Sorry, but it is given there, no, actually. If it is not given, then we'll consider as scale. Okay, fine.
No, like, can you repeat yourself?
So what I am saying, pre-stressing steel and steel is given there, no, in the option.
Yes.
If in that option it is not given, then we'll consider it as a steel.
Yeah, so that is what I am saying. Like, because see, pre-stressing steel has a higher tensile strength. Okay, so it was provided to confuse you.
No, actually, I have seen pre-stressing steel. This one is 190, and whereas for steel it is 200, I think.
Where can you kindly share the
Modulus
source?
Modulus of elasticity. Same, sir, for both.
What is the source? Can you kindly share that?
Yeah, actually, earlier I was saying, where I don't know actually.
Okay. I think.
Actually, I remember for pre-stressing steel it is 190, whereas for steel it is 200.
Okay, so
that's what I remember.
Oh, you can check that once again, sir. But I think
okay.
For steel we consider it as same. So even in this particular this also.
Okay.
So yeah, let me show it to you.
It is given above steel, I think.
See, so this is what is here is the ultimate strength. Okay, so if you look at the this particular slope provides the modulus, and they are same. They are almost same actually. Okay, so in the almost pre-stressing steel and steel they are same, and then we have the CFRP, then AFRP, and then the GFRP. Okay, so for all practical applications, usually the modulus of elasticity of steel is considered same, irrespective of the different types.
Okay.
Yeah, thank you. Moving to the last question.
Right, it is given different, then we have to select pre-stressing steel this one, huh? If it is not given, it is not equal to, then what we have to do?
No, it is generally equal to, because all types of steel, because this is one theoretical question, does when you change the grade of steel whether the modulus of elasticity changes or not. So we consider it to be constant for all practical purposes.
Okay.
Yeah.
Thank you.
Thank you. So one last question regarding the cold twisted bars. Identify the incorrect statement.
It is answer B.
B, okay. B for Bangalore.
Yeah, B for Bangalore.
Okay, thank you for the response.
As well as A also.
Okay. Okay, so since we are running short of time, I will give the answer. So it was the right answer is option B, and this actually I put it because you had to listen to the lecture very carefully, because professor mentioned that cold state does not mean sub-zero temperatures. So it just refers that it is not high as what we used for the HYSD bars. So the remaining options are correct. And yeah, so with that we come to the end of the question and answer session, and I thank you all for joining. And if there is any feedback from this week's of interactive session, I welcome you all to share with me. Again, as I was mentioning earlier, the point of having this interaction session is 2 points. Firstly, we want you to prepare you for the assignments and give a feel for the theories that are discussed using some problems. So I hope that I'm able to meet the purpose for which we are joining for the weekly meetings here. So any suggestions, comments, feedbacks? Feel free to let me know if there are any suggestions. If not, we can wind up the session.
Yes, sir. We'll continue.
Okay, thank you all so much for joining, and I look forward to meeting you all next week, and we'll be doing covering the concept of durability in concrete. Okay, thank you so much.
Yes.
Good night to all of you.
Thank you so much.
Thank you.
Next.
Yeah, good night.